Today, we'll consider three topics. In the first topic, we'll discuss about non-uniformly distributed loading. So, in previous lecture, we discussed only about uniformly distributed loading, and it was relatively easy. But today, we're gonna consider distributed loading with different, force per uh, force per length distribution, and we're gonna have a little bit more complexity today, and we'll consider some cantilever support and simple supports together, and then we're gonna discuss about the point moment and hinge and point force example problems. You may downloaded the supplementary for lecture 11 where I solved some example problem. Today we'll try to consider a little bit more complex example problem, including point moment, hinge, and point force. Then, as a last topic, we will discuss about one example beam design problem. So let's begin from the first topic, which is non-uniformly distributed loading and cantilever support. So here the problem is relatively simple. We have a typical cantilever beam, and the length is L, and we have distributed loading in the length of A from the left end, and left end is free end, so that at free end there is no side wall, so M must be 0, and free end we don't apply any external force for this problem. So at the free end we can have like a zero reaction force, V to be 0. And the difference between the current example and previous lecture is that now we have quite large distributed loading at left hand, but this distributed loading decreases and it becomes exactly 0 at x equal a. Let's take this as x equals 0 and this is as x. Then you can write down this as w0 minus x over a and w0. Then you can represent this distribution mathematically as a function of position from the left hand. Now this problem asks us what will be the shear force V and moment M diagram. It simply means that we want to obtain V as a function of x and M as a function of x. The first step is, of course, we have to solve the statics problem, I mean general physics problem. Like we have to get reactions at supports. So if you replace this support rigid wall with reactions, we have to include both moment and the force. Okay, so let's say this is MC and this is CY. Then when you look at this problem and recall what you have done back in general physics, when you have these kind of loading, you have more loading here, less loading here. And if you think about statically equivalent problem, what you do is you simply take the center of this distribution. So center of this distribution will be 1/3 of the distance. Because when you think about center of triangular area, it is located at 1/3 of the height. So what you can do is you can locate this as like equivalent loading, and the magnitude of this loading must be same as the average of W0 over the entire length A. So maximum is W0 and minimum is 0, and it's linearly decreasing. So the total no, it should not be I think it must be more accurate. You have to multiply average distributed loading and the area, or in other words, you simply do integration over the entire loading on the area A. Then it will be same as 1/2 W0A. Okay, so what I mean by statically equivalent is that whether you solve this problem, the reaction at C, CY, and MC must be same if you replace this distributed loading using point loading. Of course, bending of this problem and bending of that problem is different. So in final answer, after obtaining MC and CY, you have to always go back to the original problem and think about how you obtain the Vx and Mx. However, when obtaining MC and MCY, it's more convenient to use statically equivalent problem. Okay, so please don't get confused. Okay, so the only thing you can do is obtaining MC and CY. After obtaining MCN and CY using statically equivalent problem, you have to go back to original problem and solve the VX, MX for original problem. Okay, yeah, it's a similar discussion was done in previous lecture. Whether you consider this problem or that problem, yeah, if overall force on the top is the same, yeah, the reaction at these support are same. However, because they have different force distribution, their bending shape will be different. Okay, so yeah, we are doing same thing, but when you have non-uniform distributed loading, yeah, you gotta be careful about making and constructing statically equivalent problem. Now, for this statically equivalent problem, to obtain CY, you have to consider the force balance in y direction. So you have a downward force half W0A, and you have upward force CY only. So CY must be half W0A. Regarding the MC, yeah, it's relatively simple. So let me see how they set the yeah. So yeah, we have to consider this calculation at point C. Yeah, you do the summation of a moment. So with respect to this point, point C, you have MC, which is the reaction at wall. You have this force, half W0A multiplied by LA plus L minus A plus 2/3. This is the length from the last point to C. So if you sum up these two, it must be 0. So MC must be minus half W0A L minus A minus 3 after massaging this equation. So with that, you can obtain the reaction MC and CY. Okay, so after plug these reactions into the original problem, we'll try to use 3 rules. Okay, so how to apply 3 rules? Rule 1, rule 2, and rule 3. First, we have to check the boundary condition. So at A, we have B must be 0 and M must be 0 because that is free and there is no point force at A point. And at C, we just obtained, we found that at C point, CY turns out to be half W0A. However, if you recall the sign convention for V, we set this as positive V. Okay, so when you say V at C, we have to answer negative half W0A because the force at the right end pointing upward, and according to this sign convention, you have to have minus half W0A as an answer for V. And regarding the M, we have this as positive sign convention. So when you have this MC, MC turns out to be negative number. So your MC will be it's clockwise and it will be half W0A L minus A/3. Okay, so according to our sign convention, it is a minus sign, and we have minus half W0A L minus A/3. Okay, so this is the boundary conditions. After setting up the boundary condition, then you can obtain Vx from V prime x equals to B minus Qx relationship. Okay, so this is the final free body diagram, including the reactions at C, reaction force, and reaction moment. Okay, then if you obtain Vx, it looks like this. So at the left hand at A, as I told you, V is 0. At the right hand at x equal C, it's negative half W0A. And in between B and C, there is Qx turns out to be 0. Between B and C, you see that the slope must be 0, so that you keep V constant from A to A, this area. Now from A and B, you have like a large slope, large Q, right? You have small slope, small Q, from A and B, and the slope decreases from large value to small value. Okay, and the Q is positive number because it's downward. So because Q is positive number, V prime must be negative number. So it begins from large negative slope, smaller negative slope, and as it approaches to A, the slope must be 0. Okay, so this is how you can draw V. I would say more like a graphical method. Instead, what you can do is, at least for this 0 to A zone, you can do this integral as I just told you in the beginning. So V x1 is 0. V at A point is 0. So you simply obtain V by integrating this, then integrating Qx, and Qx is written as W0 minus W0 AX. Okay, then if you plug in this and obtain the integral, it turns out to be minus W0x plus W0 over 2A x squared, in analytical equation. Having obtained the V diagram, let's try to obtain M diagram. We can obtain M diagram from this relationship. M prime equals to be Vx, and let's check the boundary condition. At A point we have M equals 0. At C point we have minus something M. So we have 0 at A point. We have minus MC in the x equal L point. So within this zone, from 0 to A, we have expression for Vx, which is this. Vx equals to be this. So within 0 to A zone, when we obtain Mx, we plug in this, and this is what you're gonna get. And from A to L, we have simply constant V, and the V is constant as minus half W0A. We simply plug in this relationship. Of course, please be careful. Here, when you do integration from A and L, you have to do Mx, and you have to do Mx equal A point. You have to always consider this difference and do integration from A to L. Okay, so please do not be confused about this. So when you look at this relationship, it only considers the difference between 2 points. Okay, so after plugging the numbers, you can obtain analytical expression within this zone. You can obtain analytical expression of M within this zone. Of course, we can obtain this a little bit more graphical method. From L point to A, what you expect is slope must be constant because V is constant. From here to there, V was 0, which means that slope was 0, right? However, as you increase the x, you have larger value of larger magnitude of V, so you can expect increase of the slope. And another thing you have to be recognize from the rule is, when you consider rule 2 and rule 3, when P is 0 and when M is 0, you should not expect any discontinuity in V and M. So when you go back to our problem, we don't have any point moment, we don't have any point force. So that from A to C, because we don't have any point force and point moment, V and M must be continuous distribution without any discontinuity and jump. Okay, so with that, we can obtain the analytical expression. And even though we are lazy and don't want to obtain the analytical expression, we can obtain like a graphical distribution of M and V out of the rule 1, 2, 3. Okay, so with this, let me finish my first lecture on non-uniform distributed loading. The only new idea compared to previous lecture is that when you encounter non-uniform loading problem, please try to obtain like the center of this weight, and you try to devise statically equivalent problem to obtain CY and MC more easily. After obtaining CY and MC from statically equivalent problem, go back to the original problem, and from original problem obtain the V diagram and M diagram based on rule 1, rule 2, rule 3, and that is it. Okay.